Alright, this next section is 7.2, and it talks about areas in a plane. So we're talking 2 dimensions. If we have 2 curves, one like this, and say the other one is like this. And let's say that we have this interval from A to B. And we want to know the area between the 2 curves. Well, we've used some rectangular approximation methods here, and we get our rectangles. And we know that if we do these rectangles, we add them all up, and the width between them is that delta x. So we have a width of the rectangle, which is our delta x, and then we use the height of the rectangle. Well, if this function is f of x, and this function, we'll call it g of x, then what's the height of these rectangles? Right, it's f of x minus g of x. So this is our height of the rectangles, f of x minus g of x. So for each one of these rectangles, our area is going to be our f of x minus g of x times that delta x. And then we're going to sum them all up, right, from k equals 1 to whatever our n is. We'll put our little k in there. And then we take the limit as n goes to infinity, and now we have Riemann sums. So what we end up doing is we're taking an integral from a to b of the function, the top function, minus the bottom function, with respect to x. And this gives us our area. So this is the area between curves. We take the top one minus the bottom one, and we integrate it over that function. So let's do an example. Let's say we have the function y equals x squared minus 1 and y equals x plus 1. Now, the easiest thing to do is to put this on your calculator, and you get your parabola here, and you get your line here. And on your calculator, when you graph these, remember you can find these intersection points. Because when we're looking, if they just say find the area between these 2 curves, then what they're asking for is the enclosed area. So this enclosed area between the 2 intersection points. So what you can do is plug these in your calculator and find the intersection points, and that's going to give you what you're integrating. So go ahead and plug these into your calculator and find the intersection points. Alright, so you should have found that it intersects at x equals -1 and at x equals 2. So those are our 2 intersection points. Now the whole way across, the line is the top one, so we're going to integrate from -1 to 2 of the top function minus the bottom function. And then, of course, that's with respect to x, because what we're doing is we're imagining these little slivers of rectangles here, and our width of our rectangles are delta x, so it's our dx. So we go ahead and simplify this a little bit. -1 to 2, we have -x squared, and then plus x, and then we have plus 1, and then plus another 1, so we have plus 2 dx. So we take the antiderivative, and then evaluate that from -1 to 2, and plug all that in, and you should get 4.5. Go ahead and pause it and make sure you actually get 4.5 when you calculate that all out. All right, so you should have gotten this, and it would be units squared because we're talking area. Now, sometimes you're going to find that it doesn't work out quite that neatly. Let's say we want to look at between y equals x squared, y equals negative x plus 3, and the x-axis. So we draw a picture. It's always best to at least sketch out a picture, even if you're going to graph it in your calculator, which I do suggest that you do because you're going to want to find the intersection points. But the sketch on your paper will help you see where you are finding area. So we've got our line and our parabola and the x-axis. So what we're looking for is this area right in here between these three functions, two lines and a parabola. Now what you might notice is that right here we go from having the parabola on the top and to having the line on the top. So here we're going between the parabola and the x-axis, and here we're going between the line and the x-axis. So what you have to do is split it up. So we split it up by finding this intersection point. So you go on your calculator, graph it, find the intersection point, and you'll see that it's at 1.303. So all we have to do now is integrate it in two parts. So we do this first part here. We're going from 0 to 1.303, and then our function on the top is x squared, and then the function on the bottom is 0, y equals 0, because the x-axis is y equals 0. So we don't really need to put minus 0. And we're doing that with respect to x. Plus, then we're going from our intersection point to where this crosses the x-axis, which is at 3. This one crosses at 0. So we have the line on the top this time, and then minus 0, so we don't need that. So we take our antiderivative. This one we're evaluating from 0 to 1.303, and then take our antiderivative of the next part. And this one, when we're evaluating from 1.303 to 3, calculate that all out, and you should get 2.177. So pause it, make sure you actually get that. All right, so splitting this up was one way to do this, and it worked out for us. But what happens if we're going the other way? What if we decide instead that we have two functions, let's say they're like this and like this, and we want to find the area between some point here D and some point here C? Well, we can also do our rectangles this way, except what do you notice about the width of the rectangles here? The width of the rectangles here are delta y's. So what we need to do is get our functions in terms of y. So let's call this f of y, and this one g of y. And we can find that our height is still f at y minus g of y, because we go right to left. And our width of our rectangles are delta y. So when we add it all up, we can get our area, it would be the integral from c to d of f of y minus g of y dy. So we can do this with functions in terms of y as well. So for this one here, let's erase all this. If we do this particular problem with respect to y, then we don't have to break it up, because if you look at it, excuse me, on the right hand side we always have that line y equals negative x plus 3, and on the left hand side we always have that y equals x squared. So what we need to do is see if we can do this in terms of y by getting our functions in terms of y. So here we've got y equals x squared, which means for this part here, this side here, we have x equals the square root of y. Now over here it's the negative square root of y, of course, but we don't need that because, excuse me, because we're starting at 0. So we just want the positive part. And then for this line here, we can solve it. So we have y minus 3 and then divide by negative. So we end up with x equals negative y plus 3 for this function. So now what we have to look at is what are our bounds from this part here down to here. So this is our y interval. So here we looked at from 0 to 3 on the x because we did it in terms of x, but this time we're going to do it in terms of y so we can do it all in one integral. So what you do is we look at our calculator and we see that, well, we start on the x-axis because that was given in the problem, and then this intersection point, we saw that the y value, when you find that on your calculator, is 1.697. So that means that we are going to do an integral from 0 to 1.697, and we do the right-hand function minus the left-hand function, and now we're integrating with respect to y, because our little width intervals, the amount we're counting off on an interval is all along the y-axis. So you can just plug this into your calculator and do it, or you can go ahead and find your antiderivatives, but either way you'll find that it's 2.177 just as we got before. So make sure you actually do work out this problem. Pause it now and go ahead and make sure you get this. So why would we want to do this? Well, obviously this is a little bit easier because we only had to do one integral. When we did this with respect to x, we had to do two separate integrals. So this way we can do it with just one. So areas in a plane. If you're going to do it with respect to x, you go from the bottom, you take the top one minus the bottom one, and integrate along the x-axis. So you set up your intervals along the x-axis. You use your calculator to find those intersection points so that you get the area. To do it along the y-axis, you take the right-hand function minus the left-hand function, so we get a positive height there, and we can calculate out with respect to y. Now, you need to pay attention to your picture. When you sketch it out on your paper, that's when you're going to be able to decide whether it's better to go with respect to x or respect to y. When we get into doing volumes, it'll be very important to see how that you can do these with respect to x and y, because it'll make a big difference in how easy the problem is. So read the section 7.2. Make sure you've got some notes. If you have any questions, write those down so that you can ask them in class.